Welcome to the Technology Serving Humanity podcast from the FedEx Institute of Technology at the University of Memphis. In this series, we explore how innovation shapes and is shaped by our shared human experience. Through conversations with thought leaders, scholars, and changemakers, we look beyond the technology itself to examine its social, political, and philosophical impact on individuals and communities. Thank you for joining us as we explore how technology can serve not just progress, but people.
Good afternoon and welcome. So today's lecture is part of the Technology Serving Humanity series at the University of Memphis. The series explores how technology shapes and is shaped by human experience. So in an age of rapid innovation and environmental uncertainty, the series invites us to think critically about the social, political, and humanistic dimensions of technological change. The event is also connected to the Environmental Humanities Research Cluster, which at the FedEx Institute, which I co-lead with Yang Kwon, who is sitting in the front row. He's a faculty in Earth Sciences, I'm a faculty in History. And so the cluster brings together faculty across the humanities, social sciences, and STEM fields to examine human-environment relationships across time and space. And so a central part of our group's initiative is building a strong integrated research and curricular program, equipping faculty, students, and the public with the knowledge and skills to address urgent environmental challenges at local, national, and global levels. And so this talk is one part of a two-day sort of event for our group's series. So it is especially fitting then to welcome Brandon McDonald, Rumsey Family Assistant Professor of Classical Studies at Tufts University, with appointments in environmental studies and history. So Brandon's research examines human-environment interactions in the ancient Mediterranean, with particular focus on climate change and infectious disease in the Greco-Roman world. He is co-principal investigator of a late antique excavation project at a lagoon near Istanbul and has conducted fieldwork in Turkey, Italy, Egypt, and Greenland as part of an ice core paleoclimatology team. So his work has appeared in leading venues, including the Journal of Interdisciplinary History and the Journal of Egyptian Archaeology, and he is currently completing his first monograph, Pestilence in Antiquity, the Expansion of Infectious Disease in the Greco-Roman Mediterranean. And so today's talk exemplifies the interdisciplinary approach at the heart of the series and our research cluster, demonstrating how historical inquiry and environmental science together deepen our understanding of environmental change across past and present. So please join me in welcoming Brandon McDonald.
Hi, everyone. Thanks for the introduction, generous introduction, and thanks for the invitation, too. This has been great to meet some of the students here and just chat with some new friends and colleagues. So for the sake of time, I'm just going to get right into it. You'll notice that I changed the title of the talk slightly. I removed the today because I realized I just didn't have time to talk through from antiquity through to today. So we're just going to focus on climate environment in the ancient Mediterranean. So this is what the agenda is going to look like for the talk. So we're going to go through some Mediterranean geology, and I promise it's not just because Amanda's here, but because I think it's really important to understand just the structure of both climate and environment in the Mediterranean and the ancient Mediterranean, and just a bit on physical geography, climate, ancient climate, and how we reconstruct these things, climates and environments, and how we detect its influence on ancient societies, and then we'll just finish with some concluding remarks. So why are we starting with geology? Well, in my opinion, we have to, in order to understand Mediterranean climate, we have to go through much back than antiquity. So the Mediterranean was not just culturally diverse or complex, it was geologically one of the most complicated regions on Earth, and still is. And that geological complexity underlies everything, pretty much. So its coastlines, mountains, rainfall patterns, river systems, even its mineral wealth, right? So I've been diving pretty deeply into this lately, and I'm just geeking out on it. And once it's funny because once you start looking at it, you really can't unsee just how foundational it is to everything that goes on in the Mediterranean region today and in antiquity. So we would say that climate doesn't really sit atop a blank canvas. It sits on tectonics, right? And the Mediterranean exists because of long-term interactions between these tectonic plates, these major tectonic plates, specifically the African, Eurasian, and Arabian tectonic plates. So this isn't a stable continental interior, right? It's a contact zone. We have to see it as that. So over millions of years, these plates collided, they subducted, they fractured, they uplifted, and the result is this progressive continental growth that filled in what was used to be the ancient Tethys Ocean. So to understand the Mediterranean, we need to briefly visit that ocean in the Jurassic period. So now during the Jurassic period, which is the age of the dinosaurs, or early age of the dinosaurs, this vast body of water called the Tethys Ocean separated Africa, Arabia from Eurasia. And as plates shifted, that ocean was gradually broken apart. And over time, fragments of the Tethys Ocean became the Indian Ocean, became the Black Sea, the Caspian Sea, and eventually the Mediterranean. And Africa continued to kind of drift northward, eventually narrowing and partially closing this seaway. So what we call the Mediterranean today is a geological remnant of this ancient oceanic system. And as this happened, internal basins started to take shape. So as tectonic pressure reshaped the region, the Mediterranean fractured into these multiple sub-basins. In the west, you have the Alborian and Algerian basins, and in the center, you have the Turanian the Turanian and Ionian basins. That includes the Adriatic and Ionian seas. And in the east sits the Levantine basin, which includes the Aegean Sea. And these are not just geographical labels, we can't see them as that, where they reflect distinct tectonic and sedimentary histories. And those differences matter for coastlines, they matter for harbors, ecological diversity. And now the rock record tells us something important about climate too. So much of the Mediterranean landscape is built from these Mesozoic sandstone, limestone, and dolomite deposits, right? And they were deposited when large parts of the region were shallow, right? It was during this phase called the Mediterranean salinity crisis, right, where the Mediterranean almost disappeared. So over millions of years, water erosion carved these into dramatic karst landscapes in places like Greece. We're thinking places like Albania and Turkey, for example. These places are flush with caves. And those caves contain speleothems, or for our purposes, stalagmites and stalactites, which preserve climate records that we use to reconstruct ancient precipitation and overall wetness patterns, typically, sometimes temperature, but more related to wetness. So even the rock record itself becomes a climate archive for us. But these sedimentary formations, they also tell another story. Now, so we saw how the Mediterranean is a collision zone, right? And Africa pushing into Eurasia. And that collision crumpled the crust and produced the major mountain systems that we have today. Think of the Alps, right? The Apennines, the Atlas Mountains, the Taurus Mountains, and the mountain ranges of Greece. And these mountains are geologically pretty young, and in many places they're still active. So mountains, they shape climate, right? They force air upwards, producing rainfall on one side typically and drier conditions on the other. And they feed rivers through snowpack and glacier melt, and they create sharp microclimates over very, very short distances. So before we even talk about temperature and rainfall trends, we need to recognize the Mediterranean the Mediterranean climate is structured by pretty rigid topography. Now, igneous rock is nearly ubiquitous in the Mediterranean. There are huge granite outcrops in places like Egypt, Spain, Corsica, and Sardinia. Ancient societies exploited granite and other igneous rocks extensively for architecture and monumentality. And these rocks are directly related to the region's tectonic activity, especially in the central Mediterranean, which is one of the most volcanically active zones in Europe. So we have to think of volcanoes like Mount Etna, Vesuvius, Santorini, Stromboli, which are just as active today as they were in antiquity. And these volcanoes are not peripheral, right? They're integral to Mediterranean environmental history, which we'll talk about in a little bit. But first, let's move to the southeast, because something else tectonically dramatic happened there. Now, in the southeast Mediterranean, tectonic tilting in the Oligocene epoch lifted ancient crystalline rock formations upward. So this exposed what we call the Nubian-Arabian shield. And these are these rocks that exist in this shield themselves are incredibly ancient. We have to think of the pre-Cambrian era. So this is like the earliest age in Earth's history, like starting 4.5 billion years ago. But their exposure actually happened much later. So when East Africa began to rift, right? So the rifting, it formed the Red Sea, but it also exposed granite, porphyry, gold, and gemstones, and large amounts of them, what we have to say, which brings geology or geological history directly into ancient economic history. So the eastern desert of Egypt became a mining and quarrying zone for Roman imperial building, right? Really important for these purposes in the Greco-Roman period, but particularly in the Roman period. So the mining of precious minerals like gold expanded in Greco-Roman times, and granite, porphyry were extracted in huge quantities for Roman imperial monuments like the Parthenon in Rome. And that rifting event that created the Red Sea led to it becoming a corridor, right? A really important corridor or gateway that linked the Mediterranean and Indian Ocean worlds. And all this depended on that tectonic drifting and rifting that occurred millions of years earlier. So we can say geological deep time, it structured ancient economic possibilities, right? And by the time we reach antiquity, the Mediterranean is already an extraordinarily structured environmental system, right? So why does all this geological information matter for climate, right? Well, these tectonic collisions, they create mountain barriers. Mountains structure wind patterns and rainfall. Basin formation shapes coastlines and circulation. And desert formation, it structures aridity gradients. So in short, Mediterranean climate is not just atmospheric, it's geological, right? And as climate in the Mediterranean, it just only makes sense when we understand the tectonic skeleton that lies beneath it, right? So just a bit on physical geography. The Mediterranean, it's 46,000 kilometers of coastline, right? So it's extraordinarily fragmented along these coastlines and in its interior. And it includes peninsulas, islands, archipelagos, and natural harbors. So from limestone cliffs in the Adriatic to volcanic slopes in southern Italy to these North African sandy shores, this is not a uniform seascape whatsoever, right? So this irregularity mattered enormously for settlement, right? It mattered for natural harbors that helped generate urban density, and this made maritime connectivity easier in some places and really hard, much harder in other places. Now, much of the land immediately inland is rocky and pretty mountainous. These ranges acted as both barriers and corridors, but they also fed rivers, importantly. So several major rivers shaped Mediterranean societies, we could say. Now we have the Rhone and the Po rivers, and they connected the Alps to the western basin of the Mediterranean. And the Ebro River in Spain structured Iberian landscapes. And in the east, you have the Nile River, which stands apart in both scale and importance. And many river systems created wetlands and marshes and environments that were both agriculturally productive, but also epidemiologically significant, which we'll talk about later in this presentation. And yet, despite these rivers, much of the Mediterranean world is defined by aridity. We have to remember that. So large parts of North Africa and the Near East are arid or semi-arid, right? Which you can see in these two images here. The Sahara forms a massive ecological barrier south of the Mediterranean coastline. And in Egypt, habitable land was largely confined to the Nile Valley, the Delta, and some scattered oases in the Western Desert. So even before we talk about climate trends, we're dealing with a region of sharp ecological contrasts, right? We have coast and mountain, we have river and desert, and connectivity and constraint all within that. Now to talk about climate. So the question is, were climatic conditions across the Mediterranean region broadly similar? And the short answer is no, they weren't. Now, before we even get into this, we need to distinguish between Mediterranean climate and the climates of the Mediterranean region. So Mediterranean climate is a technical category in the Köppen-Geiger classification system, right? Which you can see here highlighted in orange, and it's restricted to mainly the central Mediterranean. Now, it refers to a climate defined by hot, dry summers and cool, wet winters. And the pattern exists not just in certain areas around the Mediterranean Sea, but also in places like California, thinking parts of Chile, South Africa, and Australia all have this climatic label, this Mediterranean climate, right? But the Mediterranean region itself is not climatically uniform. So it includes areas that do not fit this classic pattern at all. So what we have to say is that we're not dealing with a single climatic zone, we're dealing with a climatic mosaic, which I think this figure represents pretty clearly. So the central Mediterranean, that is like Greece and southern Italy or parts of coastal Turkey, they fit this classic Mediterranean climate pattern or model. And when we think about northwestern Europe, which is on the left here, this is a temperate oceanic climate. Central Europe is more continental in climatic character. We're thinking like north of Italy. And Egypt on the right here, and much of North Africa are dominated by desert conditions. So even within relatively small distances, at least relative to the Mediterranean, or relative to the globe, climate conditions can shift pretty dramatically. And this makes the Mediterranean a micro-regional climatic world, which is what I think we need to see it as. So when we talk about Mediterranean climate and antiquity, we have to specify where. We can't just assume that it was all the same because of this Mediterranean climate label, right? So what drives climate in the Mediterranean? Well, we have several atmospheric systems influencing the climates that materialize in the Mediterranean Sea. So we have the North Atlantic Oscillation, or the NAO. This affects winter storm tracks. And we have the El Nino Southern Oscillation, or the ENSO, that has teleconnected effects in our region. So that means basically places very far from the Mediterranean influence its climate. And then we have the Indian Ocean monsoon system, influences Eastern Mediterranean environments, in particular the Nile River system, hugely important to Greco-Roman societies, which receives its waters far south of Egypt and in the highlands of Ethiopia. And westerly storm systems from the Atlantic bring much of the Mediterranean's winter precipitation also. So we have to say the Mediterranean sits at the intersection of multiple climatic regimes. And that makes it dynamic, but also makes it sometimes unstable. So the question becomes, like, how stable were these patterns in antiquity, and have climates changed a lot since then? Well, in broad structural terms, the Mediterranean has been long characterized by strong seasonality. Okay, summer dryness and winter precipitation are not modern inventions, and we have desert zones in Egypt and North Africa. They existed in antiquity too, right? So the basic atmospheric architecture of this region has deep historical roots that has remained largely the same up until today. But within that structure, there were indeed fluctuations, such as notable variability in precipitation, and we have significant multi-decadal cooling and warming episodes. We have big-time volcanic eruptions, and shifts in storm intensity as well. So the story is not one of total climatic transformation, it's one of variability within a long-standing framework, right? And there are a few major phases of climate change in our period that we'll focus on. Which brings us to reconstructing ancient climates and environments. So we reconstruct these things, so we were able to tell what climates and environments were like way back in classical antiquity, and see these big changes there through paleoscientific evidence. And we reconstruct climates in particular with what's called paleoclimatic proxies, right? So these are natural archives that preserve records of past climate. Now, tree rings are pretty much our best source for reconstructing temperatures. They can be really precise, right? They can tell temperatures down sometimes to the year or even season. And they've been able to tell us about major climatic phases like the Roman climate optimum, or RCO, and this is my ChatGPT rendering of Roman agriculture, right? This is not what it would have looked like, right? They wouldn't have cultivated in togas. So the RCO refers to this period roughly between the last centuries BCE and the 2nd century CE, around the mid-2nd century. And it's characterized in many regions by relatively stable, warm conditions, less climate-driving episodes, and in some areas, pretty favorable precipitation patterns. But the RCO is certainly not a uniformly benign climatic phase across the entire Mediterranean. We could say that, but in several regions, micro-regions, we'll say, it coincides with agricultural expansion, demographic growth, and the consolidation of in particular, Roman imperial power, right? So these things are aligning. The virtual polar opposite of the RCO is the late antiqual ice age, and then the Lalia. And this is a near century-long cooling episode that started with one of the most frigid decades in the past 3,000 years, in the 540s I'm talking about. So it was very likely triggered by a cluster of major volcanic eruptions around 536 and 540. Those are the two big ones. And then there are others, later eruptions that extended this Lalia, this late antiqual ice age, further into the century. So we'll see exactly how eruptions affect climate in a second. But for now, we could say that tree ring records, they inform us about these phases, about the RCO and the Lalia, in particular the warmth from the RCO and the really big reductions in summer temperatures caused by the Lalia, or coincident with the Lalia. But we need to be cautious with how we use these data, in particular tree ring evidence, but all really temperature data, because we only have a few of these data sets that extend back to antiquity, and they're from pretty specific regions, which are marked here on the map. In the Asian or the Central Asian evidence, I couldn't even fit on the map. So we should say we have to be pretty cautious using them as indicators for temperature everywhere in the Mediterranean region. They do broadly align, though. It's just we can't assume that all these places in between were the same, right, that these records are reading. So the takeaway here is that while these records broadly correspond, there aren't many of them, so we can't assume that trends were the same all around the Mediterranean just through these records. Now, we also use sedimentation stratigraphies to reconstruct both climate and environment. We extract what's called sediment cores, and these are basically just long cylindrical sediment samples from lake beds, places like peat bogs, also marine floors. And this is where sediments have accumulated layer by layer over centuries or even millennia. So sediment cores preserve sequential records of hydrological conditions in lakes and river networks, as you can see here. This is actually the excavation site that I was telling that Amanda mentioned, which I'll show you more on in a bit. And they can tell us about, say, historic environmental characteristics like erosion, flooding episodes, things like that, vegetation, sometimes even pollution. These sediment cores capture. They also allow us to reconstruct changes in rainfall patterns over time, and in some cases, evidence of land use, temperature, and just broader environmental conditions. They're quite useful, mainly relating to wetness, but they do have these other indicators, right, or indicators of other things. But we also need to be really cautious in how we use these things too, and not apply certain records for the wider region. And the best example of this is the southern Levant, where lots of different sediment core records exist, and they show just how diverse this region is, even miles apart, right? This is a really unique region, mountainous, right, but also has deserts, and just the hydrological conditions are not the same everywhere here. Like I said, even just miles apart, it's quite different. So the bottom line is, overall, for paleoclimatic evidence, I think we could say that we can talk confidently about climatic trends in microregions that we do have evidence, but we should be really careful in applying that to everywhere, right? We just need to extract more data is the takeaway before we start assuming things. Now, we also use ice cores to piece together environmental trends, but we say trends or events of a different kind. So the main cause of climate change in antiquity was not human activity like today, right? It's triggered by climate drivers. So solar activity is one important climate driver. Now, the sun goes through phases where the little nuclear explosions that are constantly happening at or near its surface are more or less intense, right? And this affects temperature on Earth through solar radiation received from the sun. And volcanic eruptions were the other big climate driver impacted climate in antiquity. And how this works is when a volcano erupts, it shoots huge amounts of chemical debris into the atmosphere, right? And that debris, which includes large quantities of sulfur, it circulates in the stratosphere for around 2 to 4 years, but sometimes in really bad cases, up to 10 years, if the eruption is big enough. But more closer to the 5 range, 2 to 5 range. And these chemical particles have a reflective effect on the sun, and this in turn cools the planet, or certain places on the planet. And these eventually, these particles, the volcanic particles, they eventually fall to Earth and are preserved in polar regions like in the ice sheets of Greenland and Antarctica. So we drill ice cores at these polar regions and other places that have glaciers like the Alps to extract information on the chronology and intensity of past volcanic eruptions. And I was part of one of these ice coring expeditions 4 years ago in Arctic Greenland, and the project was led by ice core scientist Joe McConnell, who's the top name there, and we were funded by the National Science Foundation. So our research area was a region of northeastern Greenland called Tunu, and it was here that myself and 8 other people we embarked on extracting an ice core that extended back about 4,000 years. So we're thinking like around Pharaonic Egypt. We didn't get that far. The ice core started breaking up as we went deeper because we were actually sitting on top of the northeastern Greenland ice sheet, which makes it more brittle. This ice. So we were able to get back to the Hellenistic period, but not the Pharaonic period, unfortunately. This is our last day on the ice here, and we are all like looking very haggard, and we haven't showered in like 6 weeks. And I'm on the left over there with a big beard that's now long gone. And to get there, we had to fly into Kangerlussuaq, which at the time was the only place in Greenland that had a large enough airstrip that could land C-130s, these big military planes that carried all of our gear. And since then, there's been a new airstrip added, but Kangerlussuaq was actually a remnant of a U.S. Air Force base, which had this landing strip. So we landed there, and then we had to travel to Egrip, which is a Danish research station, in order to do our staging. So that way we can get to the site, which is Tunu 2022 marked on the map there, and that's where we were drilling. And we were probably the only ones, I won't say only ones ever, but pretty much the only ones ever to actually settle at that site for a long period of time, right? There's nothing else around for hundreds of miles. So in order to get there, we had to take one of these DC-3 planes, multiple trips. Actually, this was probably the most dangerous thing of the trip. Like I was part of the plane crew. We were going back and forth four times to unload our gear. And the other half of the crew went in these 2 ice trucks, right? So they brought some of the gear that couldn't go on the plane. And when we get there, we were setting up our gear. This is us setting up the tent. And this is the tent officially up. And then I figured I added this after we had our discussion on dung before, but I figured I'd show you some other areas around the site. This is our bathroom and kitchen tent, and that's my tent up there is quite the scene. And then we got to drilling eventually, and we pulled out cores in 1 meter long sections. We packaged them, and then we stored them in ice trenches so they wouldn't melt in the sun. And until we needed to bring them home, load them on the plane and bring them home eventually. So once we actually get back to the U.S. at Joe's lab at the Desert Research Institute in Reno, Nevada, we set out to analyze the chemical signatures in each layer of the ice core, and this is done through a system called continuous flow analysis. So this works by melting an ice core gradually and channeling this meltwater from the core through really highly sensitive instruments, right, that measure these chemical components. So they're measuring volcanic sulfates, they're measuring trace metals like lead and dust and things like that, just atmospheric processes. And it does this at an extremely fine resolution, right? So it allows us to detect these year-by-year changes in atmospheric conditions, basically. And this is our eruption chronology. So I focused in on the 6th century here for a very specific reason. But I'll show you why this matters in a second. I just wanted to show you what our chronology actually what it looks like from these cores, or this core. So ancient DNA, moving on to this really quick, is our other major paleoscientific source of data that we use to reconstruct just ecological processes, right, in antiquity. And it's especially useful for detecting ancient pathogens that cause big disease events, right, like epidemics and Mediterranean-wide pandemics. So ancient skeletal material, so especially teeth, can preserve trace fragments of pathogen DNA, right? And usually this is only the case in really well-preserved environments, but ancient DNA analyses and research is getting way better. So usually you couldn't find this stuff in arid environments, and most recently it seems that we have found something in an arid environment. So the field is progressing pretty rapidly. Now, archaeogenetic researchers, they extract this DNA from these teeth usually, right? But other dense parts of bone also contain DNA. So they're extracting it from the skeletons, right? And they sequence it to identify these specific microbes that infected individuals centuries or even millennia ago. And in some cases, pathogen-positive skeletal evidence, they align with references from ancient authors that talk about these big plague events, right? And it thus adds hard biological evidence to events documented in text just millennia ago, right? So it's really adding a lot. It's filling in big holes, right, in our history. Now, how are we measuring influence? So in some cases, the influence of climate was comparatively good, right? Like the period of the Roman climate optimum, or the RCO. So, and it's assumed that this was quite good for the Roman period in the Roman world, because it coincided with agricultural expansion, demographic growth, and just really the general expansion of the Roman Empire. While in other cases it was notably bad, like during the late Antiquity Ice Age with the Lalia of the 6th century. So we have texts from ancient authors that talk exactly about what seems to be the very beginning of this cooling episode that is defined as the late Antiquity Ice Age, and they talk about its impact on agriculture. So these 6th century sources in particular are describing an extraordinary dimming of the sun in 536. So what they say is that the sunlight weakened, right, to almost like an eclipse-like state for months or even a year in some cases, and it was accompanied by unseasonable cold, as well as crop failures and just widespread anxiety. And how they frame it is like a terrifying portent, right? So we have to. So even though they're framing it like this, we use these stories and we look at them and then we align them with the actual scientific data, like I was showing you before. And what it actually seems to be that they're seeing is a prolonged atmospheric disturbance consistent with a major volcanic cloud, very likely the eruption that kicked off this late Antiquity Ice Age or Lalia. And this is indeed confirmed by ice core evidence. In particular, we can see it in our ice core record for volcanic activity right around 536 here. It aligns almost directly with these ancient references. Okay, so we that's easy. We had texts, right? We had the scientific data that aligned with it, but what happens when we don't have written evidence? What do we do? So in most cases, we go to archaeology, right? And this is exactly this human-environment interaction or human impact due to environmental change. This is exactly what we're aiming to do in an archaeological project that I'm involved in or co-leading in Turkey, in Küçükçekmece, which is a lagoon that is just west of Istanbul. And we're setting out to answer this exact question, the impact of environment on this settlement. So just for some background, our site focuses on it's a Greco-Roman site. It's located pretty close to, old Constantinople. And the site's history spans from the Hellenistic Greek period through to the medieval period. So there's a lot of phases here. Now, it was a harbor city and it was located along this river network, right? And this is really important because this river network once connected the Black Sea to the Sea of Marmara, right? So we have to see this barrier here as open, right? This was once an inlet to the Marmara Sea, which is linked to the Mediterranean, of course. And it operated as kind of like an alternative shipping lane to the Bosphorus, right? So it was quite important. And it had a good relationship with Constantinople based on our material evidence. But yeah, this river network had silted up over time. And once it did, it totally transformed the nature of the settlement, right? We can see this in the material record. So this suggests, this silting that we see here, right, that a major phase of either climatic or environmental change happened, right? And like I said, it totally changed the nature of the settlement, the constitution of the settlement. But we don't really know when this happened, right? So this transition made what was a well-connected harbor site into basically a landlocked site, right? So one major goal of our project is to figure out, how this happened and when this happened. And in terms of climate environmental reconstructions that we're going to do to help answer these questions, we're extracting sediment cores, which you can see on the left figure here. These are little red and black circles. These are places where we're extracting cores. And we're also taking speleothem samples from a cave in the region, which is highly unusual to have a cave and speleothem samples, directly on site, which is almost like a kilometer just north of the lagoon, right? Don't tell anyone this because this isn't published yet. So we're really hopeful that these environmental proxies that we extract will hold some good data, right, to help answer this question of like water balance and the erosion and sedimentation of the lagoon, well, what now is the lagoon. So then we're going to move to archaeology. This is typically how you do this, right? You especially like in many cases where we're doing geophysical surveys around the site to see where is best to start digging, right? Now we've already started digging, but we started exploring other areas, right? And these geophysical devices, what they do is they basically send radar signals into the ground, right, that tell us about the structures beneath it that we can't see, right? And these geophysical surveys will give us a good indication of where to start digging, usually in areas that have more concentrated material or architectural remains. So then begin systematic excavations. This is us across a few seasons, actually. A couple of these are actually, most of these are 2023, summer 2023. And after we kind of do those systematic excavations, we use those data on Earth to start reconstructing ancient settlement patterns, right? And then we analyze architectural fragments to tell kind of what building techniques they were using, what materials they were using, right? And if they're from the wider region or they're from the locality or the wider region. And we use coins and other small finds for dating and to do economic transactions and patterns. And probably our most useful source of evidence is pottery and other ceramics, which reveal things about commercial connectivity. That is the type of relationships that this specific site or specific sites had with other settlements in the Mediterranean. And our site seems to have had a pretty good connection with the Levant, with Egypt, with Constantinople, of course, and some areas from Greece, but also some connections in the Black Sea region, which was a really cool find. And when you combine all this stuff, right, when you combine the environmental, the settlements, the economic data, a picture hopefully should emerge of how the function of this ancient site and ancient sites more broadly, how they are evolving or resilient to this type of environmental change, right? This is a pretty drastic example, of course, but this is how you would go through this. This is at least how we're going through this. Okay, the last section of the talk. So how climate change impacts disease ecologies. Now I'm going to use I used one of Kyle's figures here, who he was a co-author on. So climate drivers and climate. So we say climate drivers and climate change, how they affect disease. They do so, we could say, in three pretty important ways, which is reflected on this figure here. So they do so at the pathogenic level, right? So prompting infectious microbes sometimes to evolve. At the host vector level, and this is done by impacting the environments of the animals harboring and spreading these pathogens, and at the societal level as well, through affecting our food supply, also affecting, this can affect or this can drive migrations. It can affect our nutritional status, right, and thus our immune systems. And in antiquity, we have four pretty big events, right, and this last one here, the Justinianic plague, is one we're going to look at closely now. So this happened right after the late Antiqual Ice Age, right? Like a few years, so a year or two. And the Justinianic plague, just generally, what we could say was that it was a Mediterranean-wide pandemic. It first started in 541 CE with this devastating 4-year-long outbreak, right? But it had around 15 additional outbreaks or recurrences over the decades. Sometimes some people say more, some people say less. This is really based on the textual record. But we also have, this is all reflected, I should say, by these little circles and years, right? These are textual references. But we also have aDNA evidence, and that's these colored boxes here. So this is skeletal evidence that tested positive for a pathogen dating to the period of the pestilence, right? So proving that the causative agent was Yersinia pestis, or bubonic plague, which is the causative agent of the Black Death, right? Now, the main reservoirs of bubonic plague are rat fleas, especially, and rats, but more particularly for the ancient period, probably black rats. So the plague cycle, how does this usually work? Well, we have the bacterium. It's existing enzootically, or we could say like endemically, but usually when we're relating to animals, enzootically in wild rodent populations, right? And the bacterium passes between wild rodents with the flea, with the help of the flea, right? Which is acting as a vector of this bacterium. But sometimes those wild rodents, they'll stray from their natural habitat, right? And they'll move closer to us, they'll move closer to our animals, and move closer to the commensal rodents that live around us too. And big shifts in climate or environment which impact vegetation is precisely the type of trigger that can drive plague-bearing wild rodents towards us, we'll say. Now, the ways that climate influences the flea are particularly interesting. So we were talking about this earlier in Amanda's class, but the bacterium, it can only infect or colonize fleas and turn them into the spreader of plague under very specific environmental conditions or climatic conditions. So what lab studies have shown is that it can't be too wet, it can't be too dry, and importantly, it can't be too hot, right? So specifically, it can't be over, say, around like 80 degrees Fahrenheit, or the bacterium, it just won't be able to infect or colonize the flea, turn it into this transmitter. And in such cases, when it's just too hot, bubonic plague epidemics, they usually peter out, right? Because the bacterium just really struggles to infect the flea at high temperatures, and without it, it can't really spread very far, right? So in this way, a shift in climate can stomp out plague epidemics, or it can lower environmental guardrails that normally keep the bacterium geographically constricted to certain areas and allow it to spread more widely. And it's this latter scenario that may link the Lalia to the Justinianic plague. So the question is it just a coincidence that this acute 6th century cold phase, is it a coincidence that it started just before the outbreak of this devastating Mediterranean-wide disease event? I mean, I don't think so, but I have to be we should say correct and say that we really can't, we don't have enough evidence to say definitively that they are linked. And this is something that I and a few others are working on right now, actually, in a publication. But as of now, we can't say definitively that there is a connection. But I like to think that there likely was a connection, right? Just because of the reasons I told you. So, okay, what are the big takeaways from all this information that I just tossed at you? So I think we can say that, ancient Mediterranean, it was not one big homogeneous climatic zone or ecological landscape. It was pretty significantly varied, right? Had all these microecologies. So natural archives, what we learned, they're a pretty valuable source for reconstructing past climate, but they carry some pretty, we should say we have to be cautious with their use and how we interpret them, because it has limits. And climate drivers, they impacted ancient environments to the variability or stability in several ways. So in terms of agriculture, right, related to the environment, but also pathogenetically and epidemiologically. And climate environment, we should see, I think, as equally influential to ancient civilizations as war, politics, economic structure, and religion. And I think research on ancient environmental history, it needs more people working on it than there have been. I think like ecology it's foundational, to the way these societies operated. And even the slightest shifts, we'll say, to the natural world could throw a wrench into the mechanics of that underpin their ancient societal systems, right? So yeah, this is a plea to get more people working on this, right? And thanks very much for your attention. I'm sorry if I went over. No, not too bad. Okay, thanks.